The previous lecture, I have already covered the principle of differential protection. Today, inshallah, which, as I mentioned, it requires two settings, which is the slope. Okay. So I need for a differential, I need to know two quantities as input and two settings. The first setting is a minimum current pickup setting, which is in the y-axis. This is the differential current, and the x-axis is the restraint current. And the restraint current is, as it increases, it will restrain relay from operation. And the ID, the differential current, is the operating quantity. As it increases, it will tends, the relay tends to operate. And now for bias differential protection, we choose a minimum pickup setting for this differential in order to overcome like errors between the differential current, between the two currents during normal operating conditions, during no load conditions. So like in a transformer, so in transmission line, sending and received end is not equal. There is a charging current in the capacitance, shunt capacitance. So we have to have a setting is higher than 0 with a percentage. So we say we choose this as IS, the minimum pickup settings, and some differential relays. This you have. This is one thing. This is one setting. So the current I different has to be greater than this, as well as it has to be greater than a current, differential current in proportion to the restraint. So this is the second one, which is another equation like this. Okay, so this is equation is KIR, ID equal KIR. When I say KIR, ID greater than this means ID greater than KIR means it is here, up above this line. When ID greater than IS means above this horizontal line, so I'll get a relationship something like this. Okay, so this is a single slope, and this slope is the K. So I have you need these two settings, IS and the slope. And for these two quantities, that this is the settings, and the slope, and the two inputs for a relay. Okay, is the, or it calculates I differential, which is I1 minus I2, and I restrain, which is the average of the two currents. Okay, the magnitude of the two currents average. And this is the principles of differential relays. Now, these characteristics can be indifferent. They can be two slopes. Okay, it can be starting from here, just a slope with minimum current. Okay. But the principle is I need to know I differential and I restraint. This is for biased differential. Okay. Now let's apply this principle on transformer protection and generator winding protection. So inshallah, I'll try to cover today the transformer protection. If I have time, try to cover the generator protections. For transformer, we have special difficulties as compared to if we compare it with other types of protection, like the motor winding protection or generator winding or bus bar protection. One of these unique issues with transformer, the input current is not equal to the secondary current. So in another way, if I choose CT ratio here, same CT ratio here, I will have a differential current to U2 currents. They are not different, even during normal operating conditions. So I have to take this in consideration. I have to take a CT ratio that, you know, eliminate this difference such that the secondary current here is equal to each other, although the primary is not the same. So I'll use difference CT ratio. This is a solution. Now, a second problem also, that if I have a star delta or delta star, or a transformer that has the current in the primary is not in phase with the secondaries. For a star delta or delta star, I have 30-degree phase shift between the primary and secondary currents. So as a result, even if I made this I secondary 1 and I secondary 2, okay, is same in magnitude, but they are not in phase. If you subtract them, they are not equal to 0 also. And I have to also make them also in phase. So these two I1 and I2 that will go to the relay has to be same in magnitude and in phase during normal operating condition. The third problem with transformer, if you have a tape changer, okay, the transformer ratio will change also. Suppose I select I1 and I2, I corrected the magnitude during the normal tap or the nominal tap, okay, of the tap changer transformers, and already I corrected also the phase. But when you change the ratio, okay, then that will alter the current, so that will create also a differential current due to tape changer that you have covered in Power Systems 1. We have to have a tolerance, okay, that this differential relay can still maintain its secure or accurate operation, even if you have a degree of error due to change in transformer ratio during normal operating conditions. The fourth issue, we have the inrush current. Inrush current is a current, once you switch on, if this transformer offload and directly switch it on, okay, even if there is no load, there will be a primary current and there is no secondary current. And if there is a load, then if you switch it on, the primary current will be higher, much higher than the normal current due to the energization. It's like a starting of a motor, so this is like inrush currents, and we have to that inrush current will create a difference in current between the high voltage and low voltage side, and as a result will create a differential current, and we have to deal with this, okay, by using harmonics as indicator of that the transformer are switched on or switched off, okay, sorry, switch on normally. And normally inrush currents are rich of second harmonic, so this is can use second harmonics as indicator of the presence of inrush. Now, the fault levels, and if you compare the fault currents, it doesn't have a lot of second harmonic, but inrush current is a full harmonic. This is the way we differentiate that. Oh, this is a starting current. It's not a fault, and as a result, we will develop, the logic in addition to this equation that I differential has to be greater than KIR, the slope, times IR plus IS. So I'm using this relationship, but can be also and also. So I'm using ID and IR in this logic. This is slope and this is IS. So So the relay operates here. I know this is the differential current is here, and the restraint current is here. So you are over. This is the operate region here, restraint region. Now, or I can use also the two logic that ID has to be greater than IS and ID has to be greater than KIR. Now this is the previous. Now to add security or relay so that it won't function during the inrush current of a transformer, I would add another condition instead. It won't trip just because of this. It has also to check, is the second harmonic IH2 is the current of the second harmonic, magnitude of the second harmonic, divided by the fundamental, the 50 Hertz component or the 60 Hertz components. If the ratio is higher than a setting, a threshold, then that's if the second harmonic, let's say, it becomes 30% of the fundamental. This is the 30%, means there is inrush, and if this inrush means this becomes high, this high becomes not gate here 0. So I will restrain, I will block the tripping, okay, although I have a satisfactory differential current, a satisfactory first condition. So this is how I would block the operation. I will overcome the problem of the inrush currents false operation during starting of a transformer. So we use something called harmonic restraint. Okay. Sometimes they will add also, in addition to KIR, they will add also a factor times harmonic. So there's so many. This is a big topic. Some of you can also look at it and present it. Okay. The restraints and differential types of restraints and differential protections. Now let's apply in this following example. I will not consider. There's also one more issues in transformer is the when the core saturate. This is during core saturation will add or transformer core. It's not the CT's saturation. When the core gets saturated due to that the voltage is high or the frequency is low, okay, then we use V over F ratio as indication of the CT saturation. At rated voltage and rated frequency, the flux in the core is normal, okay. When the voltage is increased or frequency drops, the fluxes in the core will get higher than knee points, and as a result, core will saturation. As a result, I would have also a force differential, and I want to detect these conditions by using the fifth harmonic. So I use sometimes in fifth harmonic to block the differential relay from being tripping the transformer and incorrectly. Okay. But I will not consider these. I'll just focus on implementing this in the following examples. Okay. This is now how I would to correct the ratios. So I'll say we have now two things that we want to correct. I want to make this current and this current that goes to the differential relay are equal in magnitude and equal in phase during normal operating conditions or during external faults. Okay, so when I say external, any fault beyond these two CT. So this is anything between the two CTs are defined as the zone of protection of differential relays. And so how do I make this two currents are equal in magnitude? And as I mentioned, and we have to make to correct the phase shift if this is delta star by using, if this is delta side, I will use star here, and the delta and the star side I'll use delta connection. With this I will correct the phase difference between this. So this signal becomes in phase with this. The second thing I would like also to correct the magnitude. This magnitude has to be same as this magnitude by choosing proper CT ratio. Okay, I'll show you now how do we correct phase and magnitude in old types of relays, in electromechanical relays. We use sometimes something called interposing CTs. Okay, ICTs. So this interposing CT will correct the phase and magnitude. We can connect the, although this could be a star delta or delta star, okay, we can connect these CTs as a star, star, and we correct the phase and magnitude difference using this another transformer, another CT, which correct the magnitude and phase. Okay, now let's take an example here. See, sometimes we cannot really make this exactly equal to this, okay, because we don't have standard CT ratios that for all values of currents. So I'll show you an example. Suppose we have a transformer star. So with a star, then I have no problem with phase shift between these two currents. But suppose now the transformer rated voltage is 115 this side and 220 kV, 20 kV this side. Okay, 115 kV to 20 kV the other side, and the 75 kV rated power. And now to choose this ratio CTs, I have to find the rated current at the primary I nominal 1, and I have to find the rated current at the secondary I nominal 2. Okay, and I nominal 1, I have the rated power and rated voltage at the HV side. I can find the nominal current. So S over root 3 V line, which is 115, it gives me this current at the HV side. At the LV side, this is the LV side, which is 20 kV. Also same S, which is 75 divided by root 3 times the 20 kV LV voltage. That gives me 2165 ampere. This is the primary and this is the secondary current at the transformers terminals. Now, what will be this secondary current at the secondary of the secondary current of the current transformer at the two side? Now, based on this full load current, what's criteria 1 to choose the CTs? I will choose a CT ratio higher than this. This is criteria number 1. So I choose, let's say, 400 to 5 for CT at this side. Okay, I'll choose now higher than this, so 2500 to 5 at the second side. Okay, if I choose these two ratio now, okay, I choose these ratios accordingly. Now, what will be the secondary I1 and I2? In this case, I will divide IN1 divided by this CT ratio. IN1 now, which is IN1 is this divided by this ratio, I'll get this current. Okay, and dividing also IN2 divided by the CT ratio or at the LV side. So dividing this divided by this ratio, I'll get this current. As you can see, the currents are not equal in magnitude. And because I could not find a CT ratio that's match exactly this if I choose this is a ratio 376 to 5, and here 2165 to 5, this secondary becomes 5, 5, equal magnitude. And this is called the problem with uh, uh, CT ratio mismatch. I could not find a standard value close, okay, exactly same as the rated current. As a result, I will have a difference between these two. If you take 4.7 minus 4.3, I have 0.4 ampere difference as a differential current due to normal operating conditions. So I cannot set a relay, okay, that any differential currents at all trips. So I have to correct even this one, okay, before a differential relay consider this as a false. Okay, and to make these two same, I will use additional interposing CT, that this value now, this value that will goes here is, let's say, 4.3, and this value is 4.7. Okay, and I would like to make the 4.3 same as 4.7 by choosing a proper ratio here, and to make this 4.7 4.7, so the differential current becomes almost zero. Okay. Second is the vector groups of the transformer. If you from power systems one, also you have covered the vector groups. Vector groups is the phase relationship between the voltages at the HV and LV, or between currents at the HV and LV. So if it is, it could be YD11, YD1, YD0, sorry, YY0, and so forth. So that's represent the phase shift. Now, if there's a phase shift, so if the, let's say the current at the HV side is this here, and the LV side is shifted leading. So this is leading I at the LV side, leading IA at the HV side by 30 degree, for example. I have to correct this, and I can correct it also using the same interposing CT by connecting the CT as delta star instead of star delta, and that will correct the phase. So although this current is not in phase with this, but now this becomes in phase with this. So I can use it to correct the magnitude and correct the phase as well. However, this is now in electromechanical relays, so we would use interposing CT. Okay, so this is the interposing CT, ICT, to correct phase and magnitude. Okay, these are the, this is the transformer, main transformers, and this is the main CTs, and these are the differential relays, which is the 87 relay. Okay, now this is how we connect transformers, differential relay, okay, and conventional, and use electromechanical relays. However, this can be eliminated when we use numerical relays. Numerical relays, I can correct the magnitude of the current at the secondary and corrects its phase numerically inside. So I can just, magnitude correction is just you multiply by a factor. Okay, and phase correction, you rotate the vectors with an angle. So I can do this internally inside the relay without the need for a physical interposing CT. Okay, let's take an example now. For this, I'm using now conventional relay have this is the rating of a transformer. Okay, 11.5 kV at the LV side, 69 kV at the LV side. So it's DY11. D means the capital means the delta side at the HV side. So this is the delta, okay, HV side. And a small letter represent the LV side, which is 11.3 is a star connected. Okay, and 11 means the 11 means the LV side leads the HV side by 30 degrees. So it's like 11 o'clock. We took the watch. So at 12 o'clock is here. 12 o'clock represent the HV. And at 11 o'clock.
دكتور الجروبينج هاي
grouping is vector groups. So that's 11. So like imagine you have a clock with numbers. So this is the 12 o'clock, always pointing towards the HV side as our reference. The LV can be at 1 o'clock, at 2 o'clock, at 3 o'clock, okay, at 4 o'clock, 5 o'clock, 6 o'clock, 9 o'clock. Now, this is 11, okay. If you divide now 360 degree divided by how many 12 hours, I get each hour 30 degrees. So we can say now at 1 is 30 degree, at 2 means there is a phase shift between HV and LV 60 degree, at 3 means there is a 90 degree phase shift, and so forth. Okay. Now to say leading or lagging, so this is the vector rotation is this side. Now for the LV at 11 o'clock means LV leads HV by 30 degree. So where is the LV? LV here. So LV now, for this transformer, LV leads, okay, the HV currents by 30 degree. This is what DY11, okay. So I have this relationship. So I have to, so if I even use a CT ratio here, this current will lead this current by 30 degree if I didn't correct the phase. So I want to determine this ratio. What is CT1 ratio and what will be CT2 ratio? Determine the current transformer ratio and connections and how you will connect CT1 and CT2. Required, okay, in order to set the differential relay, the CTs with ratio in steps of 50 to 5 up to 250, and then increase by 105 in steps. So this is just give you just availability of the ratio in the market. Therefore, it should be used electromechanical relays with a variable percentage characteristics. So I will use a percentage characteristic. This is what it means by percentage characteristics, ID, and this is IR, and this is the percentage characteristics. Okay, just a slope here in this case. Okay. Now, there's no minimum settings of current for percentage differential. The variable current tab, the available current tab settings are 5.55 to 5.5 and so forth, up to 5. This is now, I don't have interposing CT. The relay manufacturer give us inside the relay settings that tabs that you can change inside the relay to correct the current, okay, to closer to 5 if it is not 5. Okay. So this is internal inside the relay that you can change the tabs to correct the currents to make them closer to the other side current. How we'll get started now. How do I choose CT1, CT2? I have to find the nominal current first. Okay. So this is the connection of a star delta, which makes LV leads HV by 30 degrees, which makes the dy11. So as you can see here, this is delta at HV, so it is delta at the HV side, okay, and star at the LV side. So it is a star here and delta here. And this delta, this current is IA, right? But this current now is IA minus IC. This is IC, okay? Sorry, IC is this direction. So this is IC, this is IB. So this is IB and this is IA. So this is IB minus IA. And similarly for the other currents. So as you can see, IA here and IA here in phase. So this IA is not in phase with IA minus IC. Now if I, as a vector groups, if I say this is IA here, IB here, and IC here. So I'll put a small letter better. So IA for LV side, IB and IC, which is this IA, small letter. Now, where is IA minus IC at HV? IA minus IC is somewhere here. So this is IA minus IC at the HV side. I would say IA minus IC. All right, so as you can see now, this current, the current will go to the CT at the HV side is not equal in phase with the current that goes to the LV side. And at the HV side, this is now HV, right? Current. This is LV current. And as you can see, the LV current leads HV's current by 30 degrees, which makes this connection is dy11. So this is dy11, okay, connection. As a result, I have to, if I use now, how do I correct this phase? By changing the connection. So instead of at the star, I will connect this main CTs as delta. And as the star, at the delta side, I'll connect these main CTs as a star, okay? And as a result, and also when you connect this, make sure also that this current, let's say now, suppose this is now phase A. Phase A current is IA minus IC at the primary. It will be also IA minus IC at the secondary. So current leaving a dot corresponds current entering a dot. So the current will be in this direction, right? Of IA minus IC and proportional to this. And but this one, it also has to be IA minus IC by connecting these CTs in a way that gives you same phase. Okay, so how do I make this same phase? I'll connect them also as a delta in such a way current entering here correspond current leaving, current leaving, current leaving. Okay, and what is the current? So I want to compare this.
دكتور
نعم.
دكتور احنا مو قلنا دكتور انه من اذا كانت دلتا ستار بنخليها ستار دكتور، يعني الدلتا عند اللو فولتج مش المفروض نخليه ستار دكتور عشان نخلي، والعكس عند الهاي فولتج عشان نخليهم ان فيز؟
لا، نخليهم معكوسين. we reverse. if this جهة الدلتا we make a star
ايوه
وجهة
مظبوط.
star. Yes, we did this.
هذا اللي انت بتسويه هون يعني دكتور.
أيوة.
يعني دكتور هي دلتا واي، يعني انت على عند اللو فولتج حتحط توصل ستار، وعند الهاي فولتج
اللو فولتج is star connected.
ستار. اوكي تمام.
فوصلت هاي دلتا. اوكي.
خلاص اوكي تمام.
Okay. It is a star, right? It's already star. So it is a star connected. You don't get confused with this. Maybe you are looking to this, right? That's why you say delta is this side. No, this doesn't mean the
مظبوط دكتور.
sequence. Okay? Delta means delta of the HV. If it is capital letter, means HV side. So the HV side, which is the 69, is connected at delta. And this is a common mistake student does also. Right? So the first letter doesn't mean the left side, okay? It means the HV. The second letter for the LV connections. So this is LV. That's why it's a small letter. This is HV connection, okay? And this is the phase shift between the LV and HV. Now, with this, as you can see, if this is IA, okay, right? If this is IA, and this is IC, this becomes IA minus IC. All right, so which is same as this. So they are in phase, okay, as a result. So corrected the phase, so made them they are in phase. As a result, I have no issues with phase, but I have problem with magnitude to be corrected by adjusting the internal tab of the differential relay. So the first step I'll do, I'll find the nominal current at the HV, nominal current at the LV side and HV side. So just divide the rated power over √3 rated voltage. I got this current at the LV side, this current at the HV side. And now from which we choose the CT ratio. So the closest higher ratio goes to 1600. Okay. And the closest this ratio I'll choose 300 to 5. Okay, and I will connect this delta. Okay, at the HV side, delta connected, and this is a star connected. Okay. Now, because of this, what will be the current at the secondary here? It will be this current, rated current, over the CT ratio, I'll get 4.71. And if you divide also rated current to 251 divided by this, I'll get this current, which is 4.8. I'll get 4.818, sorry, ampere. All right, now, but this is not the current that will go at this delta side connected. This is the current that will go for the relay. It is not 4.71. This is what it goes. It will go 4.71 times √3 because this is connected as delta. So if you multiply 4.7 at the relay side, at the relay currents, the relay current is this. This current that goes to the relay, and also this is the current that's also to the relay. So at the relay side, at the relay side of the HV, so of the LV side, this current I have multiplied by √3. So it is the current, the primary current divided by CT ratio divided by multiplied by √3. So this current is just 4.771 times √3. I get this 8.15. But this one already, because it's star, there's no requirement to multiply by √3 or divide by √3. So it will be the one that will go to the LV HV side. relay current at the HV side is same as the secondary current of the CTs. Now, and because this is 8.15 and this is 4.18, there will be a big differential current. And to correct this, there is an internal inside this relay, a tab, that will correct this into the, so you make this closer to this. So I will choose now what I wanted. It depends on where the tab are located, right? Sometimes I correct this to 4.18, or sometimes if the tabs in this side, I'll correct this to 8.15. So suppose the tabs, now what I want to do, the actual currents ratio is this 8.15 divided by 4.18, and I want something x to 5, because x means I want to choose, is it 5, 5.5, or 10? 2, 5. So I choose the higher divided by the fixed current. So this is unknown, and from which if you solve this, you need a ratio of 9.75, okay, to correct the currents. So I'll choose here a ratio of 5 to 10, okay, which is closer to this one. So this is 5 to the x for us, and x now we find it 9.75, which is the closest among these, is 5 to 10. Now we are done from the connections and correction of phase, correction of magnitudes. And the only settings I have now here, this is setting normally for transformer, we choose 40% slope, okay? And if I have I settings here, we will choose I setting 20% of rated current, which is 20% of 5 IS minimum for transformers, okay? If I have I setting, I'll choose it at 20% of I nominal at the secondary, I secondary nominal, which is 5. So you are done, that's it, okay? This is the differential relay, okay? Now,
دكتور
yes.
دكتور احنا هسه خلينا ال 4.18 ل 8.15 ولا العكس دكتور؟ انت قلت يعتمد على التاب، على التاب، موقع التاب دكتور، بس
نعم.
هون في السؤال هذا يعني كيف احدد؟ هل هو لللو فولتج ولا الهاي فولتج؟
اوكي
تاب
خلينا
هون في هذا
نفترض.
السؤال.
Okay, and I will tell you why. Now, خلينا نفترض this is I1, okay, at the relay, and this is I2 at the relay side, okay. Now, when I say I1 over I2 equal شنو كريشيو، يعني يا استخدم current ratio or يعني if this represent current ratios, okay, if this represent a current ratio, means it could be either way. يعني في النهاية I have to correct either this to 8.15 or this to 4.18. It doesn't matter, okay. If I use it here, I'll make 5, you know, I'll make 10 to 5. I will divide this by half. If it is this side, I'll make 5 to 10. Okay, واضح? If it is on this side, I will make this higher. I'll choose 5 to 10. If it is at this side, I'll make this 10 to 5. I'll make it lower so that this decreases.
Okay.
All right. But in some specific examples, I will specify I want correction at this side or correction at this side. Okay. Now, suppose now I want to see how this relay will perform during short circuit. Okay. Now, suppose now, also I would like to know how it will perform during normal operating conditions. So I would like to assist this operation now. From here I have finished. I'm done from the selecting the CT ratios. I'm done from selecting the proper tab. Okay. I corrected the phase, and that's it. Okay. And now suppose now I am given a ratio. Now for this I told you for percent differential I don't have this setting. Okay. Only the slope for when I say differential, percentage differential. Okay. So you have only the settings, 40%. So we have now the slope is 40%, so k is equal to 0.4. This is the bias setting. We call it sometimes the bias setting or the slope setting. So how do I check now? I'll check, will the relay operate during normal operating conditions or not? So the trip condition here, what's this trip condition? The trip conditions here, that the trip condition relay operate when DID greater than KIR. This is the trip condition without this for percentage differential relay. What is that? So this percentage differential. Okay, so we have only this to check. So in this case, at normal condition, what is I1? I1 is this, right? It is 8 point. This is I1 that goes to the relay. Okay, and I2 is this. Now, I'm assuming now this tab is at this side. This is the tab location. Tab position at this side. So we have some tabs here. Okay, sorry, tabs at this side. So at this tab, I choose already 10 to 5. So this will increase to 8.1. I want to increase it, so I'll multiply by 10 to divide by 5. So the current here now, this current after the tab, it will be 8.36. And this is, I have no tab this side, so it will be same as 8.15. It doesn't matter, even if the tab is here, then I'll do this 8 times 8.15 times 5 over 10. I will indicate where is the tab location, okay, in problems. Okay, if the tab's on this side, I'll say 8.15 times 5 over 10. It gives me, okay, the current, and this will be same without 10 over 5. And now, this is the corrected currents after the tab. So what is the differential current? The difference between this current, differential current magnitude is this. And the restraint current is the summation of the magnitude over 2, the average of the two currents magnitudes. This is the restraint current. And I will check this condition. K times IR. K is 40% times I restraint is 8.25. I'll get this current. Now I'll check, is this current, is the ID greater than IR? What is ID? Is 0.12, is not higher than KIR, so relay will not operate. And this is a correct action because I have no fault. I'm just checking the operation of a relay during normal operating condition. Okay, this is correct action. And now suppose I have a fault, a three-phase fault, faults here at the just after relay, a three-phase fault. Phase current in this fault is 10 kiloampere. Okay. So what will be now? This is external. This is not a fault here, right? It's fault outside. So the relay should not operate in this case because fault is not inside the differential, the protected unit. Okay. it's not within the differential zone of protection. So if the relay operates, then it's incorrect action. So my expectation that the relay should not operate for external fault. Let's test it. Now, the fault at the LV side, this is the nominal current. So I fault at the HV side. This is the HV. So normally HV this is at HV side is equal to 10K, right? Kilo ampere. And I want to find, this is I nominal, I don't want it. I need to know what is I fault at the LV side. So I fault at HV, I fault at LV, it is I fault at HV times the ratio, right? So you have to transfer it to the other secondary side. So I fault at HV times the 69 over 11.5. It gives me the current at the HV side, fault current. So this is also equal to this. This is also equal to that fault current, which is 60 kilo ampere. So this is also 10 kilo ampere. This is 10 kilo ampere. Now, what is I1 now? What will be the current that goes to the relay? Okay, is equal to, in this case, relay I1 is the 60 kilo ampere, which is this now LV divided by CT ratio times √3. That gives me this current. So it is 60 over the CT ratio times √3. I'll get this current. So this is the current. It's not here, so this current will be 3, 2, 4.8 ampere. And the LV side, I2, because I have a tab, okay, because I have a tab, so this current 10K here, I will divide it by CT ratio, it gives me this current, and then I will multiply by the tab of 10 over 5 to get this current, I2, to the relay. So I2 is 10K divided by CT ratio times 10 over 5, I'll get the current here after the tab, which will be 333, okay. So here, before the tab, it is 10K over 5 over 300. So times 5 over 300 will be 2 times this, which is, this current is 6.6 ampere. Before the tab. After the tab, it will becomes 333, okay, half of it. So, sorry, it should be before the tab is half of this, okay, which is 3333 over 2. Which is 166.67. This is 166.67 ampere. All right. And now after the tab is 10 to 5, so times 10 over 5, I'll get 333.3. Now I calculate the differential current, which is the difference between this current. I got this. The restraint current is the average of the two currents magnitudes. And now I can compare the trip condition. I will check the trip condition. Is K times IR greater than or less than ID? Now, the 40% of IR is 131, but ID is 8.4, and I restraint is high. So ID is not equal to, ID is not greater than KIR, so it will not operate. So this is also correct action because fault is outside. And for internal force, now suppose the force now changed to here. So force is here. What would happen now? Okay, in this case, so in this case, it depends now. Is this transformer having, I'm assuming now, the HV side is unloaded, okay? There is no source, okay? Now, if there is a source, that current also will reverse, okay? Now, assuming here, I'm just assuming to check this, the HV side has no source, just load. Okay, this is no source. So in this case, if I have just a load, there will be no current feeding from the load to the transformer fault. Okay, this is the assumption now. If I have a source, then there will be a current also fed to the fault. Okay, and I have to know this current also in order to assess the operation of this. Okay, so under this condition, what will be this current here? I that comes from this side is 0, and because of this 0, this current becomes 0, I2. So this becomes 0 because I fault here is equal to 0. I fault at HV, okay, I fault here is equal to 0 at this side, but there is a fault current here, okay. So that current that goes here is 10 kilo ampere. Okay, this current is 10 kilo ampere, still as the previous case, I'm assuming. Okay, electrically, this point and this point is same. Okay, so this is also 10 kilo ampere. Each phase has 10 kilo ampere. But this current will not reach the other CT because I have load side. Okay, I have no source at this side. This is my assumption. So what will be this current will be same as 10K over the CT ratio. Okay, you transfer this to that side, I'll get 60K. So this is a 60K ampere. Also, this is 60 kilo ampere, 60 kilo ampere. And now I would like to change this to the secondary side and multiply it by 3, right? So 60 over this times 0 to 3, I got this current. So this current is 324.8 ampere. But this current is 0. I2 equals 0, okay. And as a result, the differential current will be I1 minus I2, which is this current. And I restrain is the average of the two, which is this plus 0 over 2, which is half of it. And now if I calculate KIR as this, I'll get 65. Now, is ID greater than KIR? Yes. Okay. As a result, relay will trip. Okay, and this is correct action because fault between the two CTs, okay, which is within the protected zone. Any questions so far? Okay, now
No,
I can
Doctor,
say,
clear.
okay. Now this is another example of, now suppose I have here, and this technology, they provided me with tabs. Now suppose I have no tabs and I provided with external CT to correct the magnitude of the currents. Now this example is not exactly the same because this is rating 12.5 and the previous one was 30. So this is a different example. And this is also DY1, it's not DY11. So for the first, determine the transformer ratios Okay, the CT1, the transformer ratio and connection required for compensation for the compensation transformer اللي هو interposing CTCS. So this is the ICT. I want to know its ratio required and connection. So I want to find how do I connect this and how I also choose its ratio, which will be used for both phase and ratio corrections. I will use this to compensate phase and compensate magnitude and correct magnitude. So I will not correct magnitude, sorry, and phase here. It's already given the CT ratio here. Draw the complete schematic and three-phase connection diagram, identifying the current in each element. So I would like to see how the current flow in each part of the circuits. So this is dy11. So what does that mean? D capital means the HV side is delta. Where is the HV side? It's 115. So this is delta. And LV is LV small letter y means it's connected as a star. LV is this LV. So this is as a star. Okay. And now I connect it as delta star, and delta gives me 1, which means if I have, this is IA, IB, and IC. Okay, just practice this. I want a connection that makes the HV side. Now, 1 what is 1 o'clock. 1 o'clock means if this is a 12 HV current, LV current should be at 1 o'clock. This is the LV. And 1 o'clock means LV becomes, it lags HV by 30 degrees. So where is LV side is this LV. So now this LV lags HV current by 30 degrees. So this is what it means, the dy1. So that current, the LV, lags the HV current, which is this, by 30 degrees. Okay, so this is I LV, this is I HV. This lags this by 30 degrees. So this connection gives me this. If you look, this is I know IA, IB, IC. Okay, suppose this is IA. Okay, just practice it. You will see IB, IC because I use small letter IB, IC. So this is IA, IB, IC. And to get this IA and this IA is in phase, and so and this is IB, so this is IB, and this is IA, and so this becomes IA. This will becomes IA minus IB. So that's IA minus IB. Okay, right? This is IB, and this is IA. So this current will be IA minus IB. And where is IA minus IB? This is IA and this is minus IB. And if you add these two, I'll get a current here. So this is IA minus IB, which is the LV side. Now this LV, so the HV. The HV becomes, this is the LV, and this is the HV side. So the HV leads LV by, okay, HV leads LV, or LV lags HV by 30 degrees. This is 30 degrees, which makes the connections correct. So this is how I connected the main transformer that gives me dy11, dy1. And now, in this scenario, he wants me to correct the phase and magnitude by using this additional transformer. So I will also connect now, this is as a star-star, I'll connect the interposing CT is indicated at the LV side. So I'll connect it here at this side. And I would like to now, I don't know the ratio. I want to choose a ratio of hair turns ratio. This is a turns ratio, not the current ratio, okay? Turns ratio in this case. So if this is one turn, this will be a turn. So this is N1 to N2 or N2 to N1 or whatever. So the ratio of the winding of this transformer. And so what's the connection of this? I'll connect it such a way that this current, if this current is IA, right? This also will be IA. This is leaving, this is entering IA, this is IB, and this is IC. So if this is IA, I want this one, what is this current? Is IA minus IB, right? What is the secondary current? Is also IA minus IB. Okay, for this phase, this will be IA. So there will be a phase shift between them of 30 degrees. And to correct it, I have to make this current same as this current. So this has to be same as this, okay? And this has to be, okay, corrected. So while choosing, so what I want this current to be same as this. So what is this? I'll connect this to delta star. And the delta star, as you can see, this is IA, which is in phase with this. And this is IB, which is in phase with this. And this current will be, if this is IA and this is IB, this will be IA minus IB also. Okay, and so this current and this current that will go to the differential relay, this is the differential relay. Okay, this is the 87 relay. The current that goes to the input and the output of that relay and the two terminals of the relay are in phase now because of using interposing CT that correct the phase. Now, I corrected the phase by using this connection, but I'm not sure if the currents here now is same as the current here. I have to make these two currents not just in phase, they're also equal. So I have to choose a ratio that makes this current IRX and IRH. H represent high voltage side, X represent the LV side. Okay, and this is the terminology according to American standards. I use H for HV and X for LV terminals. Similarly for transformer, main transformers currents. Now how do I do the same? I will do the same thing now. I just connected now. All what I did here, I made the connections that correct the phase, but I don't know now how I need to choose the ratio A, 1 to A of this interposing CT. This is the ICT. Okay, and this is the relay. Now, what is the nominal current? Nominal current, as we did, I got it, this rated current at the HV side, rated current at the LV side, from which I choose the ratio. Now, in this example, it is given, but even if it's not given, this is the way I choose this. So I'll choose here 100 to 5. I choose here 600 to 5. Okay. And because we used interposing CT to correct phase, I don't have to correct this. I don't have to change the connection of the main CTs. I'll connect them as a star-star so that they don't alter the phase, because phase correction is done here. Okay, so I'll connect this both as a star. And the relay currents now, what will be the current that will go to the relay at the HV side? the current will be now the full load current divided by CT ratio. I'll get this is current. And the HV side, the full load current, which is this, divided by the CT ratio, I'll get this current. Okay. But that will give me this current, right? But I want the current at the because this is a delta connected, okay? Because this is a delta connected, so what is IRX? Because this is a delta connected, then I would have, and with a ratio of this, so I'll have like this current, what I get now. This current is I549, so this current 546.7 divided by the CT ratio divided by 600 over 5 or times 5 over 600. I get this current, but this current now I have to transfer it to this to get this current and multiply by √3 to get this current. Okay, so the ratio is unknown here. I'll multiply, because this is a terms ratio, okay, so it will multiply by 1 over A, okay, right? Like we know that in transform I2 over I1, okay, equal to N2 over N1, right? Sorry, N1 over N2, right? So N1 here is like whatever, okay. This is I2 side, this is I1 side, so this is N1, this is N2. So I got this is the current, so the current referred to the secondary side of the CT times 1 over A give me this current times √3 gives me this current. Okay. But I don't know, I want to make this value equal to this, okay? So my objective to make this one equal to this currents using a proper ratio. Now, so this quantity becomes 7.89 over A. I will make these two equal, okay, from which I find A, proper A. So the A has to be now 2.51. That will correct this quantity and make it very close to 3.14. Okay. Now, what is the actual current? Now, sometimes you don't find exactly this ratio. You will find something close. I can give you, like you have 1 to 1, 1 to 1, 1 to 1.1, 1 to 1.2, 1.1 to 1.3. So you can't choose 2.51. So either you can choose 2.5 or 2.6. You choose the closer available ratio for the interposing CT. Now suppose now I have this ratio available. Okay, so what will be the actual now current at the HV side, which is same as this because I have no interposing CT here, and the actual secondary side will be also same if I choose this exactly same ratio if it's available. But if I choose 2.5 or they will have, you know, a different, this current will be a little differential current. So ideally, in this ideal condition, when I be able to choose a CT that exactly correct the currents, then these two will be exactly same. So the differential current becomes 0, I, which is I1 minus I2. In this case, ID in this case is I at relay side at the HV side, I1, which is minus I2 at the relay at the low voltage side. This is I differential. I restrain will be this average of these two magnitudes. So this is now the connections. This is the solution of this problem. Okay, so I'm done from the settings. This is I just checked during normal operating conditions. The differential current is very small. We can then, based on the available now type of relay, what is the slope and the minimum current, I can check also whether it will operate or not. Okay, I'll leave this one as an exercise. Okay, and tomorrow, inshallah, in the next class, I will just close with these slides. Now there is another types of differential protection, which is called, which is used for air fault protection, okay? And it is called restricted air fault principle, okay? So it is a sort of differential. However, this types of protection is only dedicated of one side of the winding. Here it will protect only the star side of the transformer by connecting a CT, all the CT at the star side as in parallel here, and you take a CT at the neutral, you connect them parallel. Okay. Now this is I neutral or I ground. This is IA, IB, IC. And IC. So during normal operating condition, these currents are balanced, and the secondary currents here, if you add them also, will be zero. So this current or this current is zero during normal operating conditions. Similarly, the ground current is zero during normal, so there will be no differential current. So this is like a differential current, difference between the neutral CT and the phase CTs. Now, when there is a fault somewhere in the transformer, in the star transformer, like a fault here, okay, then I have a currents here much larger than currents in the normal operating conditions and the other phases. So if you sum these three currents now, is not equal to zero. It will be I faults. Okay. There will be something equivalent to I faults. Okay. And as a result, I'll have a differential current. Okay. And the relay, differential relay, will operate. And this is just maybe from the previous lecture I already mentioned. We have two types of principle, bias differential and high impedance. No, now this is the relay. You connect a series impedance with it as a stabilizing resistor, R stabilizing. Okay, and this is also a sort of differential, but it is only detects faults within the star. If a fault happens here, it will not operate. If a fault happens here, it will not operate. It's only when a fault in the star. That's why it's restricted. Okay? And only detects ground faults. It doesn't detect face-to-face faults. If there is a face-to-face fault here, it will not detect it. Okay? Three-phase fault will not detect this. Only line-to-ground faults. Okay? Only ground faults is going to be detected. Line-to-ground or okay. We can also apply differential on bus bar. If I have a bus bar, this is the bus bar. Okay, this is the bus bar. And these are the circuit leaving or entering the bus bar. Okay, and if you connect on each phase one CT of this feeder, we have three phases. Okay, and then you connect each phase A with phase A with phase A, okay, and goes to phase A relay, and phase B relay, and phase C relay. Okay, and as a result, you get also, this is a sort of differential protection of transform of bus bar. As you can see here, we don't have to have a ratio corrections or phase shift issues because CTs, okay, you will choose this CT to match this current, this CTs to match that current, this CT to match this current, okay. Inshallah, what I have presented only two types of protections for transformer. I presented the differential when the two CTs at the primary and secondary are connected to a differential relay, and I also presented the 64 relay, which is the restricted air fault, which is this type of. So at the star side, as you can see, I put a CT at the neutral and connected with the CTs at the star side line. So this is the restricted air fault relay, ref, okay? And this is the differential relay, which needs input from this CT and input from this CT. And there is another restricted air fault at the delta side. It is something when you connect these CT here in parallel, it will also, it is only force in the star, okay? Ground force in the delta. So this is only restricted to this side. It will not detect any force when it's at the star side. And this is also restricted air fault, okay, but dedicated for the delta side. Okay, so I'll take from the CC, but these normally different CTs we will use for this one. And there's other types of protection over fluxing protection, which is V over F principle, voltage divided by frequency, based on which I know what is overfluxing. Is it the core saturate of the transformer or not? We call it overfluxing. Okay. In the following lecture, inshallah, I will show you how do we set relays, how do you apply this relay for protecting protecting generator stator winding. Also, I would like to compare sensitivity of these two. Okay, I see the comparison with these two. The comparison, if I use just a CT here, ground fault, how do I compare this with this? Which one is better? All right. So this is what I'll do, inshallah, in the next class. Okay, I will stop at this stage. And if you have any questions, I will open the floor for any questions.